Winglets. Today we're talking about how shaping them differently affects their performance. So winglets are probably the most well-known flow control device on airplanes. And if you don't know what they are, then you probably do know what they are. You just didn't realize that they were called winglets. So to give you an idea of what they actually are, they are those little end plates that often go vertically up or down at the end of wings. And if you go to any airport or you search online for any airplane, almost all pictures of a modern airliner, except the Boeing 787, will have them. And the Boeing 787 has something quite different, which we'll discuss a little bit later on as well. But anyway, we actually covered winglets, something very similar to this, in the last episode on birds. So it's a natural kind of winglet and it's much more sophisticated than what we do. And that was pretty cool too. But in this podcast, we'll be going through our own type of winglets. And the reason why winglets are so widespread, particularly on airliners, is because they are so good at reducing drag, in particular lift-induced drag. So how do they do that? It's quite simple actually. So when you have a wing that is producing lift, you obviously need to have a pressure difference between the top and bottom surfaces. This pressure difference results in overall force, this imbalance, and that is lift. And that's great until you reach the end of the wings. Then you suddenly get this interface between the high pressure underneath and the low pressure on top, and they just start meeting. And we all know that air likes to go from high pressure to low pressure. It's kind of like me and chicken schnitzel. In this analogy, I'm high pressure and the schnitzel is low pressure, and I always get drawn to it. And as such, the air underneath the wing bleeds over to the top and a vortex is formed. Now, is this vortex really a problem though? I mean, like, it's just there minding its own business. Is it really that bad? Well, in this particular case, yes, it is bad because we're not using this vortex for anything. So in essence, this is just wasted energy that is exactly what drag is. We're not using this energy for anything other than this nice little cool feature, but it's not helping us in flying. So that is drag. So if we were to use this vortex, on the other hand, for some purpose, then that would really, I guess, be not drag. That would be some other feature. But because how it currently stands, we don't use these vortices for anything, they are drag. But there is more to it than that. They're actually bad for another reason. And that is because not only do these vortices mean that there is more drag, but when you have air from underneath circulating around to and then down on top, that means that the air near the wingtip is actually being pushed down more. And that means that the effective angle of attack drops because you have the air traveling how it normally does, but now it is also being directed downwards, which means that the angle that the wing is pitched to compared to the free stream flow is no longer the angle of attack that you set the wing at. It's this angle of attack plus this additional vector component. And this means now that the air is more in line with the wing. As a result, the effective angle of attack drops, and hence the amount of lift you produce is also dropping in this region. So this wingtip vortex is not only creating more drag, but also reducing how much lift this wing is producing. So it's like a double hit in terms of these bad features. So to prevent this from happening, we use winglets. And winglets are a kind of crude but very effective way of stopping vortices. It's actually one of those things which it's very crude, but it works out in this case. So instead of playing with the pressure distribution over the wing, which is the sophisticated way to do it, and modifying the airfoil profile or twisting it, etc., to reduce this pressure difference between the lower and upper sides at the wingtip, the winglet is literally just a physical barrier between the high pressure and low pressure sides, so that these airflows can't mix. So it's kind of like a vending machine where there's this glass plate between you and the sweet goodness, and the only way to get that goodness is to pay money. So anyway, winglets literally stop the mixing of these airflows, which stops this vortex from forming. And as I mentioned, this is a really crude way of doing it, and nature has a way better way of doing this than us, and we covered that in more detail in the last podcast. But despite being so crude, there are more ways to shape a winglet than you can poke a stick at. Like, there are literally hundreds of different ways. And you can change how big it is. You can change whether it's vertically up or down or at some non-vertical angle. That's called a Cant angle. Sorry, sometimes I call it Kant from like the philosopher Immanuel Kant, but it's called Cant, C-A-N-T. So if you hear me saying Kant in this podcast, just know I mean Cant angle. So you can change how much it's canted at. You can change how much it's swept back at. You can change its airfoil profile. You can even add a winglet to the winglet's wingtip to prevent it from forming a vortex if the winglet is producing a lift, so kind of like a mini winglet. So the question is, what is best then? And that leads us to the question of today's podcast. What cant and sweep angles should you have for a winglet? How do these cant and sweep angles affect a winglet's performance? So to answer this, we're going to look at a paper called Boogly Boo, CFD study. Let me go up a second. Here we go. CFD study of the impact of variable cant angle winglets on total drag reduction. And this is an open access paper. You can find it in the link in the description, freely available for you. Now, in this first part of the podcast, I want to talk a lot about the direct aerodynamic effects of a winglet on an airplane, because I want to lay this foundation so we understand what they do. But to have a more, so they are also a structural feature, not only just an aerodynamic feature. And I just wanted to cover this because it is often not talked about. So when you have a winglet, you have more mass to the wing. And you have this winglet at the end of the wing, which means that you have more mass pretty much as far away from the wing root as you can get, which means that the moment that you produce is pretty much the largest you can produce because it has the greatest moment arm. So is that a bad thing? Do you have to make the wing stronger to withstand this additional moment arm? Well, not always, because when you think about an airplane flying, the vertical force is up, and that is the direction of lift. So the wings bend up because of it, because you have this force of lift and it pushes these wings up. And on some airplanes, the wingtips bend like 1.5 meters. That's a lot. So for example, I remember the first time I flew over the wing of an Airbus A380, one of those big boys, and on the ground, I could look out the window and see the wingtip. But when I was in the air, I could no longer see the wingtip out of the window because the wing had flexed so much that the wingtip was now too hard to see. And even if I were to bend down, like I was like sitting down in my seat and like bending over trying to see the wingtip out of my window, but even still it was almost impossible because it was just deflected so high up. And that's how much the wingtips flex on an A380. And I don't remember exactly when the A380 came out. I don't remember if I was already doing aerospace engineering or not, or if I was still in high school. But I do remember taking it once to America, and I was going to go to Tijuana. I not really, but it's just a joke because I heard some pretty bad things about it. Like, actually, I remember talking to this one guy at an aerospace conference, like a couple years before that, who was saying that his daughter, I guess I must have been doing aerospace engineering then, he said that his daughter and one of his friends got carjacked in Tijuana. And he didn't seem too concerned about his daughter being carjacked, more about the car being stolen because it wasn't covered by insurance or something. So force majeure, I guess, I don't know. Anyway, so winglets, because of the added mass, actually help reduce the moment of the wings. So you have the lift trying to bend these wings up, then you have these winglets which are additional mass at the ends forcing these wings down. And also, if you make them produce an outwards force, so the winglets are producing lift of some kind or some kind of force sideways, then you can actually make these counter moments which actually flex the wings even more down. So because you have smaller moments of the wings, because you have more mass and this flexing out, the wings actually don't need to be as strong. So you can use less material, save weight, and increase fuel efficiency. So winglets are very complex and can benefit a wing in more ways than one. And that's what makes them so fascinating and so important to airplanes. So figure 2 shows just some different types of winglets, not all, but just some. As you can see, there are 8 here. So looking at how many there are here, this is just the tip of the iceberg. So in fact, some have been created through aerodynamic necessity, like to try to make them better. But interestingly, others have been created to get around patents. So for example, if memory serves me right, Boeing had their winglet, which they've had for ages now, and Airbus wanted to have a winglet too because they know how beneficial they are. So they decided to make different ones and call them sharklets, and that's to get around the patent. At least that's how the story goes. So actually, also, we just made a YouTube Shorts video about wings that are more than 100% efficient. It's only like 20 seconds long, and if you are interested in that, just look up on YouTube, The Impossible Wing from Aerodynamics, and it should come up, or check the link in the description here actually as well. So we go through as well, like how these winglets in the extreme form actually make the wing more than 100% efficient. And that is what winglets do. They start making the airplane, in extreme cases, more efficient than aeronautical theory can really say. So in this study, the researchers looked at this wing and winglet in figure 6. Let me scroll down to there. These are the figures that I just mentioned. That was pretty much just what I just scrolled through now. Is pretty much what I was talking about this up to now, how these vortices form, how winglets work, just in a more succinct way than that. So anyway, in figure 6, we see the Onera M6 wing, which is a wing with a 26.7 degrees sweep angle, a 0.56 taper ratio. So the wing chord is 0.5 times the wingtip chord, is 0.56 times the wing root chord. The aspect ratio is 3.8, which is quite low because a low aspect ratio comes with more induced drag, more wingtip vortex. So this airfoil is also symmetrical, which is important to note because for a couple of reasons. One, at a 0 degree angle of attack, it means this wing is not producing any lift. Two, when we have a wingtip on it, depending on its angle, it may or may not be producing any lift. Because if you have it vertically up completely and you pitch the wing at an angle of attack, still that means that the winglet is not at an angle because it's vertically up and you're just pitching it about the non-angle attack direction. But if you have it canted at a certain angle, let's say 30 degrees, and then you pitch the wing, that also comes with a slight increase in the angle of attack as well for the winglet, which means that the winglet is also producing lift. So that's important to keep in mind. Now, the winglet section comprises 20% of the entire wingspan, and it's a decent size. It's 1/5. That's quite large. The researchers looked at 3 different sweep angles to the winglet. So we see here, this winglet here was swept at 30 degrees, 45 degrees, and 60 degrees, which is quite extreme. So to investigate how these sweep and cant angles affect the wing's performance, I should also mention that a cant angle went from 0 degrees all the way up to 80 degrees, which is almost vertical. But to investigate how these sweep and cant angles affect the wing's performance, these researchers used CFD and in particular RANs. So is it okay to use RANs in this case? Well, because this is a very streamlined body at low angles of attack, in other words, the flow will be attached and well behaved, RANs is actually fine. Something that is important to note is that the Y plus was 4, but because they used the K-Omega SST turbulence model, this is okay. I mean, it would have been better if they had a Y plus slightly lower, maybe 1, but 4 is acceptable still. The K-Omega SST, the K-Omega family in general can handle Y pluses below 5 quite well. Anyway, the mesh was between 3.6 million and 4.1 million cells, which is maybe a little lower than I expected, mainly because I don't know how crisply the trailing edge was resolved, given that the wing is several meters long. And that's actually a big problem with CFD for wings. Trying to get that trailing edge refined enough is very difficult, especially how the mesh comes down. Then you get the face there, and that can create some problems. So often we just make this trailing edge a little bit blunter than being very sharp, and that helps us with the CFD. But anyway, maybe it was okay with their CFD setup. Let's go further and talk about how they set this up even more. So one good thing that these researchers did was that they made the inlet of the CFD, as shown here in figure 9, curved. So that way, to change the angle of attack, they only had to change the angle of attack of the air coming in instead of changing the airfoil and then remeshing everything and then solving it. So by making the domain curved at the inlet, they've saved themselves a lot of time and computational power. So one thing that I don't really understand though is they said that their turbulence density was 5%, which is really high for this application. So to give you an idea of how high this is, to have a turbulence density of 5% in the free stream direction at a Mach number of 0.8395, which is the Mach number here, which is comparable to airliners during cruise. That means that the free stream velocity fluctuated randomly between this value of 0.84 Mach and plus or minus 5%. So they were seeing values like down to Mach 0.8, then the next second 0.85 or 0.84, whatever, which is like a 15 meter per second change instantaneously. That is too high for airliner cruises. So typically the turbulence densities seen by them is more in the order of about 0.1%. Now, if you were to investigate this airfoil during gusts, then you could argue that 5% is acceptable, but I cannot see them saying that here, so I think 5% is quite high. So with this turbulence density so high, that would just result in skin friction drag being a little higher maybe than normal. Because this airfoil isn't going through stall, the effects of having such a high turbulence density is not going to be that pronounced. On the other hand, like let's say we had this airfoil going through stall, having a high turbulence density level would actually help prevent that to some extent. It would effectively replicate a higher Reynolds number. The Reynolds number here was about 11 million from memory, but even still, it would still have some effect. But because this airfoil is at a low angle attack, the high turbulence density level doesn't really affect this stall, this aerodynamics right here that much. So it's not too bad. Let's move on to the validation of the CFD. So overall, they had some pretty extensive data to compare their CFD results to. It's actually quite extensive and nice. You don't get this every day. The validation data was for a 3.06 degree angle attack for the exact same airfoil, and they had the static pressure coefficient distributions over the airfoil suction surface and pressure surface to compare to. So that's pretty good. And we see at different span, like different points along the airfoil span, from 20% wingspan all the way to 95% wingspan. And one major benefit of this type of data is that you can see that if there are any flow physics artifacts in the experimental data, and if the CFD matches that. So we see here there are some peaks, and we'll go through this a little bit more in detail later. And one really cool thing that these researchers did was that they solved the CFD with 4 different solvers, and one called CFL 3D, another one USM 3D, another one called Fun 3D, and their current way. I'm pretty sure the Fun 3D, that's depending on the day. Like if you're doing meshing, I wouldn't call that fun. If you're solving, that's much funner, and post-processing is even funner. So that's maybe an optimistic name, but anyway. Now, is it a good thing to do to compare different solvers and even meshes, which they also have different meshes here? Well, ideally each solver on the same mesh should give the exact same results. However, in practice, this is not the case. So once you start going into quite accurate simulations, you do get minor differences between different solvers, and this is for a number of reasons. One of the reasons why you might get minor differences is that each solver might use different defaults for their turbulence coefficients, for example, or for their relaxation factors. Or they might use second order accuracy for some equations, first order for others, and these are the defaults and you haven't changed them or whatever. That can be changed, but these are minor differences, result in minor differences in the solution overall. But another way that different solvers can give different results is how they solve the equations, and this one you can't really change too much. So I was using one solver recently, and I was watching the residuals upon starting, so I wanted to see how it was converging just to make sure that I had the right time steps, etc. I did all the calculations to make sure the current number should be good, but as you know, when you start iterating through the initial the initialization process, you can get problems there. So I just wanted to babysit it a little bit and see what was happening. Interestingly, what this solver was doing was solving some equations and iterating through them while keeping other equations constant. Then once the values it was iterating through started to converge, it then started to solve the other equations for those variables as well that they were holding constant. So then all the variables were being solved at the same time after it had gotten some of them part of the way. So this was to make the simulation more stable at the start when the residuals are usually highest. So this kind of approach can leave artifacts in the solution and cause differences at the end. Again, they're very minor, but they will be there often. And I should say that also, if you, at this point in time, if you like this podcast so far, make sure to like it, please. It makes us feel good. And please subscribe or follow to see more. But coming back to this study, these researchers not only looked at different solvers, but also different meshes. And having different meshes definitely can help alleviate these problems. Like if you have the same mesh, but if you have different meshes, they can cause even more problems or differences, especially here where I can't really see any mesh independent study. So for all I know, these meshes are just initial guesses of what the mesh should be. I don't really know if they're any good or not. But these researchers concluded that because all of the lift and drag coefficients that they obtained with these different solvers and meshes were close, that the numerical model scheme, turbulence model, and mesh resolution were adequate. Now, there are a couple of things wrong with these assertions that they just made. They just said that because they're getting the same lift and drag coefficients, that their mesh is good, they don't need to do a mesh independent study effectively. Their turbulence model is good, so they need to look at different turbulence models. K-Omega SST is fine. That's not too bad an assumption, that one, but the mesh resolution definitely is. And the numerical scheme that they use, which is simple here, RANS, is fine too. Now, that is problematic for a couple of reasons. The first is that the lift coefficient deviated by 2.5% between these different solvers and meshes, and the drag coefficient deviated up to 9%. So that is hardly similar in results. And the lift to drag ratio deviated over 10% between these different approaches. Again, 10% is a big deal when it comes to airfoils, so I wouldn't say that their numerical schemes, turbulence models, and mesh solutions were adequate. And because they don't have any flow viz stuff presented, that makes it even harder to say that because we don't know what the flow viz looks like, the flow fluid looks like, we can't really conclude that they got similar results, if they did get similar results, for the right reasons. And even if differences were much smaller, like in the order of 1%, some flow viz in key regions, like around the wingtip, would go far in convincing the reader that the CFD setup is good. Currently, they fall short on that mark. But let's move on to the wind tunnel validation data in figure 10. So this is figure 10 here. Let me zoom in a bit more so we can see better. Here we go. So they have different cross sections, as I mentioned, along the wingspan from 20%, 44%, 65%, 80%, 90%, and 95% on the wingspan, going from pretty much almost the wing root to the wing tip. Now the good news is that the trends found in the wind tunnel are definitely replicated here in the CFD. That's really nice. We see along the entire span that there's an inflection in the pressure coefficient on the upper side, this black and blue dotted line and dots. And that is all captured by the CFD. The lower surface is also well replicated with the CFD, almost doing a perfect job matching the data. Like you can see on this black line, the red dots fall almost perfectly on these lines consistently. That's really impressive. There's only one outlier, but that's to be expected. I mean, it's not going to be perfect all the time, but it's pretty impressive. However, there is a little deviation in the values on the upper surface, and there is some overshooting and undershooting, but not by much. So you can see there's a bit of undershooting here, a bit of overshooting there, overshooting, undershooting here maybe. So overall, the CFD is fairly well validated. Unfortunately though, there are no forces to compare here. So we don't know really how accurate the forces of the CFD are. It's just this pressure distribution here. But from these pressure coefficient distributions and the table in the table 3 here, this data here, I would say that generally I think the CFD is good to within 3 to 4%. And that's okay. I mean, it's not great, but it's not too bad. It's usable. I definitely don't think it's like within 1% accuracy but I don't think it's also 10% accuracy either. I think that the 10% difference we saw between the different CFD solvers and meshes, so these ones here, that was just because of bad approaches. For example, they mixed the Spallet-Almaras Thomas model with a Omega SST model. And Spallet-Almaras was okay, but kind of dated now. I mean, when it was first developed, that was around the time when you might only have a few 100,000 cells in your mesh, and we're thrilled to have a 10% error. I mean, that was like great to only have that error. Now a 10% error is not going to cut it at all. Like 1% is even reasonable. Like you want to get even better than that now. So I think that much of the error seen in this table 3 is due to different turbulence models and even different meshes. And some proof of that is that the only entry that produces significantly different lift than the other 3 was the one using a Spallet-Almaras turbulence model, which was this one here. Whereas the other 3, these top 3, used Omega SST and all got lift coefficients within 0.5%. And slightly better drag coefficients as well. So that shows that the turbulence model made quite a big difference, I think. So I think the CFD approach they used is accurate to around about 3 to 4% for the forces. So overall, I would give the CFD setup a validation process maybe 7 out of 10. There are a few things they could have done better, like a mesh independent study. Also, another thing would have been good to see is validation at other angles of attack. They only did 3.06 degrees, but they looked at different angles of attack in their results. So they should probably try to validate it to some kind of general angle attack as well there as well, maybe 0 degrees, 10 degrees, just to get a good range. So speaking of such, let's move on to the results now. So in figures 11, 12, and 13, so 11 here, let me zoom in as well. Too much? Okay, that's perfect. 11, 12, and 13. We see the drag polars for different cant angles plotted and for different sweep angles. So if you don't know what a drag polar plot is, it is when you have the drag coefficient plotted on the x-axis like here, and then the lift coefficient on the y-axis. And these plots are very practical because you can literally look at what lift you want and then immediately find what the drag will cost you, how much drag you're going to have to incur to get that lift. And this is very important for determining things like how far you can go, sync rates, and all sorts of things that are very important for flying. So while they may seem like a little cumbersome for a researcher to look at, and compared to like a simple lift coefficient plot or drag coefficient plot, in practice these drag polars are very useful. And one tip actually for immediately seeing the maximum lift to drag ratio of this entire airfoil is to draw a line from the origin 0, which is actually here, and see where the steepest slope is, where it intersects each one of these curves. That now corresponds to the maximum lift to drag ratio, and you can actually also find then what the lift is, what the drag is, and then subsequently the angle of attack that relates to. That's very important to then be able to determine like the if like, let's say you have a problem with your engines and you want to glide as far as possible, you obviously want to have the maximum lift drag ratio, so you reduce your sink rate and then you can go further, or farther I should say. So that's what this plot is very good for doing, and other things as well like that. Now in figure 11, we see the results for when the wingtip is swept at 30 degrees. So 30-degree angle here, and the cant angle goes from 0 degrees, which is almost completely flat, which is actually, sorry, completely flat, to 80 degrees, which is almost completely vertical. And completely flat is not really a wingtip, but more a raked wingtip. So remember, raked means that when you just pull the wingtip back, so it is really only swept. There's no like putting up to the wingtip kind of angle. So if done well, you can get really good drag reductions, like as you see in the Boeing 787. The Boeing 787s, typically, as far as I know, none of them still have any winglets. They're all raked wing tips. And this was a real game changer when they did it first. I remember back in like 2013 when they were sort of bringing this stuff out. Everyone was really impressed, and they actually were achieving really good drag reductions overall, not just for the wingtips, but for the entire airplane. It was like 24% increase in fuel economy. And that was like incredibly good to be able to still make that greater improvement on an airplane at that time, when airplanes had already been reiterated so many times and improved so much. And this was one of the major differences. So anyway, initially increase the cant angle from 0 degrees, so it's flat and raked, to 45 degrees, which is diagonal. Doesn't really do too much to this plot. All these points lie pretty much on each other. The drag coefficients are very similar. The lift coefficients are very similar. At higher drag coefficients, however, which correspond to higher angles of attack, the wing became more sensitive to the cant angle, and while at low angles of attack, the cant angle below 45 degrees was the same as the results for 15 degrees and 0 degree cant angles. Above, like at more angles of attack and high angles of attack, the cant angle of 45 degrees started to produce more drag for the same amount of lift, or less lift for the same amount of drag, however you want to look at it. So that means that the wing started to become more sensitive to the cant angle as the angle of attack increased. So in fact, however, there are some minor differences for these lines, but I would say that they lie well within the uncertainty of the CFD. Now, when the wingtip is canted to 80 degrees, so almost vertical, we have a very different story here. All of a sudden, this is the green line here, and the black line is for the base wing. So all of a sudden, the lift to drag ratios drop, and in fact, at very low angles of attack, the wing produces a lot more drag for the same lift. That is likely because the wingtip isn't producing much lift, but it is producing a significant amount of drag now. So because it's canted at so high angle attack, maybe that's, canted at such a high angle, maybe that is also affecting it, where now when you pitch the wing, it's not really pitching the winglet at much of an angle of attack. It's more just like pitching it in a non-angle attack angle, and that means it's not producing as much lift either. That's potentially one reason. So at moderate angle attack, the 80 degree canted wingtip performs pretty much the same as the wing without a wingtip. Now this is a little surprising to me, because the higher the cant goes, with the limiting case being vertical, the more of a barrier you get to stop the wingtip from forming, the wingtip vortex from forming. So having such an extreme cant angle doesn't seem like it would be bad to me. It should reduce the drag. So I don't know why we get this worse performance, but we do have some more information later on in this paper, and that may help us understand why this counterintuitive result occurs. Let's move on for now. So actually, one thing that I really would have liked to have seen here is something about the wingtip vortex, because I would have loved to see how these different cant angles affected it and its strength. Even just some flow viz showing how its size and vorticity were affected would have been great. It would have given us more information to figure out what's going on here. Alas, we don't have this data though. But that gives me an idea that maybe I should do that. Like I should do some simulations of this and then put it up on our YouTube channel. I mean, I'm really interested in seeing what would happen. So you could say I'm a keen bean on that. So stick a pin in that. But from figure 11, the main takeaway is the wing's performance is quite insensitive to moderate cant angles from horizontal. Then bam, once you get to quite extreme cant angles, the wing performs worse. So there's a zone there which it doesn't really matter what you do to the wing tip. You can cant it up, down, whatever. It doesn't make a difference. But then once you go higher, it does make a difference. And the same general trend holds for the greatest sweep angles of 45 degrees. So this figure 12 is when we have sweep angle of 45 degrees. Figure 13 is sweep angle of 60 degrees. But there is one main difference. As you increase the sweep angle, the wing becomes more sensitive to the cant angle, with now even the moderate cant angle of 45 degrees here. So this is now the yellow line. That starts to perform worse even at long angle attack as well. So overall, the same general trend of the wing being somewhat insensitive to the cant angle until you get to quite high cant angles holds true, but not as much, like it's starting to wear. Now, in figure 14, we see what happens when you hold the cant angle constant and vary the sweep angle. In other words, the effect of the sweep on the cant of the canted wingtip. So when we have no cant, so this top left figure here, the wingtip is just raked. Effectively, the sweep of the wingtip makes no difference here. Like we can see that they're all pretty much all lying on each other. Literally, regardless of whether you have a 30 degrees sweep angle or 60 degrees, you're getting the same kinds of lift to drag ratios, and the differences are within the uncertainty. So what that means is that for just a raked wingtip, it doesn't matter what sweep you really have, as long as you have some amount of it. I mean, maybe if you have like 5 degree sweep, it wouldn't make much of a difference to the wing performance, but anything above 30 degree sweep of the wingtip is sweep. That's for a 0 degree cant angle. Now, for other cant angles, the same applies in general, that the wing is quite sensitive to the sweep angle, except when we are at 45 degree cant angle. So this one here, let me zoom in a bit more. This is this figure, top right, and the blue line, which is where we have 30 degree sweep. Let me move over a bit. We can see this now. Okay, cool. We have 30 degree sweep, produces a decent amount more lift at moderate and high angle attack, i.e. higher drag coefficients. Now, I don't know if this is legit or just due to the error in the CFD, because the other results don't show this trend either though. So like this one, which is we have 80 degree cant angle, this one which is 15 degree cant angle, we don't see that trend occurring here. So that means that either something very complex is happening, or this is just an outlier due to error in the CFD. So from all these plots from figure 11 to figure 14, we can draw two main conclusions here regarding the wingtip. The first is that you want to sweep your wingtip, and really any amount is good. The second is that the cant angle doesn't really do much as long as you keep it below diagonal. Going above diagonal is actually detrimental to the performance. Now, of course, this is for an Aero M6 wing, and maybe these trends might be a little different for other wings, but I wouldn't be surprised if they are similar. Now, remember how we saw that when we had quite an extreme cant angle of 80 degrees, the wing performed worse? Well, figure 15 gives us some idea, like I should actually mention this a bit more. For cant angles of 80 degrees for all these ones, that's when the wingtip is quite vertical, and that's like, you'd think that's fine because you're producing a barrier for this wingtip vortex to like dissipate this, like not let it happen. But it performed worse. So why is that happening? Well, figure 15 gives us some idea as to why. So when it comes to induced drag, this cant angle should be fine, but in figure 15 we see the shock waves forming here in this orange, and we now see on the left, this is the cant angle of 80 degrees compared to the cant angle of 15 degrees on the right. For the extreme cant angle, the left figures, we can see that unlike at lower cant angles, this one here on the right, we get a new shock that forms in the edge that is now made between the wing and the winglet. So this little orange bit here, let me zoom in. This bit here, that's a new shock that we don't get for the lower cant here. So this additional shock actually tells us why we're getting a worse performance. It increases the wave drag of the wing, which is why we're seeing this drop in performance for this highly canted wingtip. It's not because of the wingtip vortex, as we might suspect, but due to the wave drag. So mystery solved. Now, in terms of just pure lift coefficient, as shown in figure 16, pretty much all wingtips increase the lift coefficient across the entire range of angle attacks between 0 degrees and 10 degrees tested. On the other hand, figure 18, down here, shows that pretty much all wingtips also increase the drag coefficient, but we still saw that the boost in the lift coefficient outweighed the increase in the drag coefficient, which resulted in higher lift to drag ratios, as we see in figure 19. So overall, the wing became more efficient. And with that minor little analysis, we come to the end of this podcast. One thing that I was a bit surprised at was this wave drag. But I still thought that this paper was really cool. I might be a little biased because I really like airfoils, but I still think that even enemies of airfoils could appreciate the use of this information. I mean, as they say, know your enemies. So if you like this episode, make sure to like it and click the subscribe and or follow to see more. And we'll see you next podcast. Actually, I should mention also that if you want to learn OpenFOAM, our course is almost ready. The beauty of OpenFOAM is that it is completely free to use and very capable software. It's like even better than commercial software in some situations. But the ugliness of OpenFOAM is that it's really hard to learn. So that's why we're making a course for this. So we literally take you step by step from installing it all the way to running complex simulations like rotating geometries with DES solvers. So industry grade. We cover geometries, meshing, solver settings, time stepping, and even how to post-process. So you can follow along with your own computer with these step-by-step modules and learn for yourself. So keep keen for that course when we release it in another couple of weeks. And that is actually the end of this podcast now. So I'll see you next podcast. Peace, amigos.